All right, on this one, it says in exercises 9 and 10, using the graph of f, determine whether dy dt, so the derivative of y with respect to t, is positive or negative, given that dx dt is negative, and determine whether dx dt is positive or negative, given that dy dt is positive. Oh my goodness gracious. So here for number 10, they give us a graph of the function, and so we're going to call it y. Okay, that way we'll be able to do the dy dt thing because we're calling it y. All right, so if y equals f of x, or y equals whatever you want to name it. They named it f, so I'm calling it f of x. According to the chain rule, I can do this. Now look, it's not the same chain rule we've written down every other time. What we've had before is we would say that dy dx equals, oh, you can too. See, y'all can see that. So what we've had before is dy dx equals dy du times du dx. Okay? Now look at the way I've written it this time. Because y is a function of t, x is a function of t, so t is the variable, not x. So dy dt would equal, and then dy dx times dx dt. Which means, when I wrote down here y equals f of x, I wasn't quite right. What's actually the variable? It's t, isn't it? Okay? Actually, if you can do the old, the strike-through looking thing that you can do in Word and whatnot, it's not really f of x. I thought it was, but it's not. Okay? Because it's all a function of t. How do I know? dy dt, y is a function of t. dx dt, x is a function of t. dy dt, y is a function of t. dx dt, x is a function of t. Everything's a function of t. We didn't get rid of x. Oh, it's right there and it's right there. I know. Just like before, we could say y equals f of x, but to do that, it was first, y equals, well, f of g of x, and that was the u, but we didn't worry about, let's not get too caught up on that notation, or not only will I confuse you, I'll confuse myself. Okay? All right. So, using the chain rule, I get this. dy dt equals dy dx times dx dt. You with me so far? Now, they say to, for part A, determine whether dy dt is positive or negative, given that dx dt is negative. So, we want to figure out what the sign of dy dt is. So, dy dt equals. All right, now we're given that dx dt is negative. So, see the dx dt, I'm going to write its sign right there. The dy dx. All right, now, this is where the notation gets confusing. I struck through that because y is a function of x, but x is a function of t. So y does equal f of t, but as an intermediate step there, remember we used to call it y equals f of u? Okay? Look at the function here. It's always increasing. If it's always increasing, what's the sign of its derivative? So dy dx is positive. Positive times negative is negative. to do part B. Determine whether dx dt is positive or negative, given that dy dt is positive. So we just substitute in a different place. We know that dy dt is positive, so I'll put in a positive sign for that. We just figured out that dy dx is positive, so I'll put in a positive for that. And now I've got to figure out what dx dt is. Well, what's it got to be? It's got to be positive, because if it was negative, positive times negative would give you a negative, but it doesn't. It gives you a positive. So dx dt has to be positive. In step A, all right, they give us that for step A. Okay? They give it to us, right? I got that dy dx is positive by, if my function's increasing, its derivative is positive. And that got me that. Then on B, they changed the rules. We know, now they're telling us that dy dt is positive, so that's just substitution. They're telling us to determine dx dt, so that's my unknown. But the dy dx that I figured out was positive when I looked here, it's still positive. That didn't change. Make sense? Okay. Now, that's the kind of problem that, you know, there's not much work to show, but there was a lot of thinking going on, wasn't there? Let's take a look at 18. The radius r of a sphere is increasing at a rate of 2 inches per minute. We're going to have to do two things here. First, find the rate of change of the volume when r equals 6 inches and when r equals 24 inches. So that's actually two things as our first thing. And then we got to explain some stuff. So let's do part A. Okay? Let's concentrate on part A. Now, little review. This section is called related rates. These problems are related rate problems. Rate means rate of change. So related rates of change. Rate of change is derivative. Related, derivatives. Related means they're in the same equation. So we're going to end up with derivatives in the same equation. Derivatives of different things in the same equation. But they're different things, but they must be what? Related. Okay? Now, before we get the derivatives in the equation, we've got to have an equation. Okay? So, we're going to try to figure out what we know, what we need to know. We're going to try to put all of that in an equation. Then we'll take the derivatives. Okay? So, what do we know? What do we need to know? Well, we know that the radius is increasing at a rate of 2 inches per minute. At a rate, that's a derivative. It's the derivative of what? It's the derivative of r. Okay? Now, if the radius is increasing or decreasing, for that matter, at a rate of 2 inches per minute, so the derivative is with respect to time, isn't it? So that means the radius must be a function of time, and that means the rate of change of the radius can be called dr dt. So when they give us the rate of change of the radius, they're giving us the derivative of the radius. And it must be dr dt because the radius is changing with time. Okay? So the radius itself is an actual function of time. All right, you with me on why dr dt equals 2 inches per minute? All right, so that's something we know. Now, what do we need to know? Find the rate of change of the volume. Rate of change of the volume. That's the derivative of the volume. We don't have to write it down yet, but what will we call the derivative of the volume? dV dt. That's what we have to find. All right? So we're going to we need to end up with an equation that has dV dt and dr dt in it. If I'm going to end up with an equation with the derivative of volume and the derivative of radius in it, don't I need to start with an equation that has volume and radius? Now, you guys had, I don't know, I guess really the best geometry teacher I've ever known is who you guys had. Okay? And he probably taught you that the volume of a sphere equals 4/3 pi r cubed. He's a wonderful man, too, by the way. Just top notch. Nothing like fishing for compliments. All right, so that's our equation that has volume and radius in it. You with me? You see where we're going with this? We've actually accomplished a whole lot. We figured out that we know dr dt. We figured out that we got to find dV dt. We figured out an equation that relates volume and radius. Now we've got to turn this into an equation that relates dV dt and dr dt. So take the derivative. What are we going to call the derivative of V? dV dt. Equals. And then on the other side, I need to take the derivative. Now, 4/3 pi is a constant. Okay? So, when I take the derivative of this, I can use the constant multiple rule. Or I can use the general power rule. Okay? Or I can use the combination rule. It's all the same thing. What it all means is I need to multiply that exponent times that coefficient to get me started, don't I? Now, if the coefficient had an r in it, then it wouldn't be a constant, and I'd have to use the product rule, wouldn't I? But it is just a constant, so I can do it this way. Back before we learned the chain rule, we would have called this the combination rule. Okay? So exponent times the coefficient, I can do that because the coefficient is a constant. So exponent times coefficient. Then I get r, and what do I do to the exponent of 3? Minus 1 times the derivative of r, because r is not a variable, r is a function. If r was just a variable, we'd be finished with the derivative, wouldn't we? But r is not just a variable, r is a function. And not only is it a function, it's a function of time. So what are we going to call its derivative? dr dt. Let's simplify a little bit. dV dt equals, well, 3 times 4/3 is 4, so 4 pi r squared dr dt. And I'm pretty happy with that. We now have an equation that relates the rate of change of the volume and the rate of change of the radius. It's a substitution game from here on out. Okay? So, back to part A. Find the rate of change of the volume, so find dV dt when r equals 6. Okay? So find dV dt when r equals 6. Even write it down so that you'll know what you're doing. Find dV dt when r equals 6. So, dV dt. All right, now 4 pi is 4 pi. But that r squared, what did they just tell us r equals? 6. So make that 6 squared. So we've taken care of everything I've got underlined in blue there. dr dt. What do I put in for dr dt? 2. That was the very first thing we wrote down. That was the first thing they told us. So put in a 2 for dr dt, and now all you got to do is a little multiplying. 6 squared is 36. 36 times 2 is 72. 72 times 4 is 288. Don't forget the pi. Now, units. I'm horrible with units, okay? Your science teachers probably want to slap me around. But I know what the units are going to be. And here's why I know what the units are going to be. When you measure volume, let's go back up here. When they told us the radius is increasing at a rate of 2 inches per minute, they told us the units, they told us that the linear unit is inches, and they told us the time unit is minutes. Well, volume's always cube units, right? So volume is inches cubed. Now, dV dt is a rate with respect to time. So volume is inches cubed, time is minutes, so dV dt is inches per minute. So, like I say, I know I don't really do what your science teachers want me to do and carry the units every step of the way. But don't forget your units. And you should always be able to know what your units are. Okay? So inches cubed per minute. With me? All right. We're also supposed to find dV dt when r equals 24. Go. What'd you get? Yep. Everybody get what I got? Now, could we find dV dt when r equals 7? When r equals 12? When r equals 32? Now that we've got the formula, we can find it for any r we want. Okay? Now, let's tackle part B. Part B says, explain why the rate of change of the volume of the sphere is not constant. And look, we can see it's not constant because when r equals 6, that's what the rate of change of the volume is. And when r equals 24, it's a different rate of change of the volume. So it's not a constant. Okay? So explain why the rate of change of the volume of the sphere is not constant, even though dr dt is constant. So, looking at this, why isn't dV dt a constant? Because r is exponential. Okay? dV dt is not a constant because it depends on r squared. I should have written as well as dr dt. I made it sound like saying that it was depends on dr dt with some revelation there. But and r is exponential. That's what screws it all up. Let's see. All right. From the ones you attempted last night, what would you like to see? I don't think I have 3 on here. I have to go to. Oh no, I just have the wrong document up. That's all. Joseph, if you have a hall pass. All right, number 3. Let's see, the direction said, assume that x and y are both differentiable functions of t and find the required values of dy dt and then dx dt. So for number 3, they give us that xy equals 4. So before we worry about answering the questions, they've given us our equation. So they're starting there with where we started, or when we got to here. Okay? We don't have to figure out what we know and what we need to know. They're telling us that. They're taking care of that for us. All right? And in fact, they've already done that step for us. They've written the equation. So we start off with xy equals 4. Now, to turn this into a related rate equation, we get rates. How do we get rates? Derivatives. Rates are derivatives. Derivatives are rates. Okay? So, product rule. Now remember, x is a function, y is a function. Product rule. First function times the derivative of the second. What's the derivative of y? dy dt. Plus the second function, y, times the derivative of the first. What's the derivative of x? It's not 1 anymore because x is a function of t. So it's dx dt. On the other side, the derivative of 4 is 0. Now, before we move on, let me emphasize to you, x is a variable unless you're told otherwise. Don't all of a sudden on the test Friday start chain ruling every time you see an x. Because up until yesterday, x was always a variable, wasn't it? It still is unless you're told otherwise. And we are told otherwise because in the directions they said x and y are both differentiable functions of t. If they didn't tell us that, we would treat x as the variable. But they told us that. Okay? So, if you've started your practice test already, make sure, unless they tell you x is a function of t, that you treat x as a variable. All right? So everybody with me on the equation? All right, we should be in pretty decent shape from here. So I didn't really know what to do with it. They tell us to find dy dt for part A and dx dt for part B. So it really doesn't matter what version of that equation you come up with because you can substitute in and solve for whatever's left as your unknown, can't you? So, you got options as far as that goes. So for part A, find dy dt. So if I'm going to find dy dt, I might as well use the form where I've got it all solved for dy dt, right? When x equals 8, given that dx dt equals 10. Now, let's see, how did I get y equals 1/2 out of that? Okay, so if x equals 8, then 8y equals 4, and y equals 4 over 8, which is 1/2. Okay, and now I can substitute in for everything. dy dt is what I'm looking for. I've still got a negative sign. So y gets replaced by 1/2. X gets replaced by 8, because they told us when x equals 8. Okay, and dx dt we're given to be 10. So everything gets replaced except for what we're looking for, the dy dt. Then you simplify. You with me on A? Then on B, we're supposed to find dx dt when x equals 1. All right, when x equals 1, what does y equal? Well, if that's a 1, y equals 4 then, right? 1 times y is y equals 4. So x equals 1, y equals 4, and we're given that dy dt equals -6. So I went ahead and used this version again. I don't know that that's the easiest version. The one above it looks like it probably would have been the best one to use. Okay, but use whatever version you want, substitute in everything you know, solve for what's left. Sounds simple, doesn't it? Is it simple? I don't think so. Some of y'all do. I don't think it is. It's logical. I'll give you that. It's logical. that help for 3? All right, what else? Lindsay? Number 6. All right, so on 6, they tell us that a point is moving along the graph of the given function such that dx dt is 2 centimeters per second. Find dy dt for the given values of x. So we have, for number 6, y equals 1 over 1 plus x squared. So let's turn that into a related rate equation. We're going to relate the rates of dy dt and dx dt, because again, they're giving us the equation that has the knowns and the unknowns in there. So dy dt equals, and then look what I have to do on the right side. I have to use the quotient rule, don't I? So that's the bottom, 1 plus x squared, times the derivative of the top. Well, the derivative of 1 is 0. Woohoo, that simplifies quite well when you multiply by 0. Minus the top, 1, times the derivative of the bottom. The derivative of 1 is 0. The derivative of x squared is 2x times the derivative of x, because x is a function of t. They told us it is. So it's 2x times the derivative of x over the bottom squared. So you with me with that first big red check mark? Now, all that goes away because it's multiplied by 0. So I've got a negative 2x dx dt over that. And that's, I mean, I don't have to leave the dx dt in the numerator. I could set it out like that, couldn't I? But that's about as good as I can do. That's a good version of my equation. Now, they told us in the directions that dx dt is 2 centimeters per second. So we're told that dx dt is 2. All right. So the first thing, well, let's see. I'll take it back. That's a good version of the equation until I realize they've told me what dx dt equals. So I take it back. That's not the best version of the equation I can get, because I can replace dx dt with 2. Okay, why leave a dx dt in there if you know it's 2? And that is the best version of the equation I can come up with. Okay? So now we're supposed to find dy dt when x equals negative 2, find dy dt when x equals 0, and find dy dt when x equals positive 2. That help? That help everybody? All right, let's see, what time? Homeroom day. Oh no, we still got a while. What else you want to see? All right, 16. It says, let A be the area of a circle of radius r that is changing with respect to time. If dr dt is constant, is dA dt constant? All right, so if we've got the area of a circle, again, in geometry, well, let's face it, even before you came to geometry, you know the area of a circle was pi r squared. So if we start with that equation, because we're dealing with rates of change of area, rates of change of radius, so start with area equals pi r squared. Now turn it into your related rate equation by taking derivatives. The derivative of A, because everything's a function of time, right? if the radius is changing size, it's got to do it in time. And if the radius is changing size, the area is changing size in time. So they're both with respect to time. So dA dt, that's the derivative of area, equals, and if r was just a variable, the derivative of pi r squared would be 2 pi r. But r is not just a variable, r is a function of time. So chain rule it, the du dx at the end is now a dr dt at the end. So does everybody understand? Because if you don't, you need to speak up. How I got that equation. Because if you can get that equation, forget the number 16 in particular. If you can get that equation, you got a fighting chance on these problems, don't you? Okay? All right, now, they want us to explain what? If dr dt is constant, is dA dt constant? No, and it's not because of an exponential this time. In fact, which problem we just do? No, it did have an exponential in it. No. Well, the easiest way I know to explain it is because it depends on more than one thing. Okay, it's dependent upon a dr dt and an r. All right, if it just depended on something that itself was a constant, it would be a constant. But it doesn't. It depends on things that change. One of them, the r, changes with respect to time. So whether dr dt is a constant or not, r is not. It's changing with respect to time. So you're not going to get a constant rate of change of the area. Does that make any sense? All right. What else? Okay. 11. All right, on 11, consider the linear function y equals ax plus b. If x changes at a constant rate, does y change at a constant rate? If so, does it change at the same rate as x? All right, y equals ax plus b. That's where we start. Does that look familiar? If they'd given you an m instead of an a, would that look really familiar? All right. So they're asking us about rates. Let's turn it into rates. So the derivative of y is dy dt. The derivative of ax. Well, the derivative of 7x is 7. The derivative of negative 2x is negative 2. So the derivative of ax is a. All right. Oh, wait, hold on. Hold on. Product rule it. Product rule it. Because how do I want to explain this? No. Not product rule. Constant multiple rule. Okay? And I can product rule it. Constant multiple rule it. A times the derivative of x. Okay? Because what I was saying before when I was wrong, I was forgetting that they told us that dx dt, or they told us that x, how do they say it? If x changes at a constant rate. So x is changing at a rate. That means x is not just the variable, is it? So I temporarily forgot that. I plead temporary insanity. I forgot for a moment that x is changing with respect to time. So since I now remember x is changing with respect to time, I've got to treat it as a function. Okay? So constant multiple rule. It'll be the derivative of ax will be a times whatever the derivative of x is. So, sorry, I feel like I let you down there. I'll try not to let it happen again. You're okay with it? It's okay if I make a mistake?
No, just don't let it happen.
Don't never do it again? No, you cannot make mistakes. Well, no, you're free to make as many mistakes as you want. And I'm free to go. All right. And the derivative of b is 0. All right. So, let's see here. If dx dt is a constant, so let me rewrite that. Let's choose k. And a lot of times k stands for a constant, right? So if I rewrote that as dy dt equals the constant a times the constant k, is dy dt a constant? Yeah. So if dx dt is a constant, then dy dt is a constant, which means y does change at a constant rate if dx dt is a constant. Okay? Now, the rates are not equal. Why aren't they? Well, they could be equal only if a equaled 1, correct? So I guess I should have thrown that in, but I didn't think of that. The rates are not equal because dy dt is a multiple of dx dt. So they're both constant rates, but they're not the same rate. Okay? The only time they would be the same rate was if a equaled 1. I feel like I butchered that. So questions on 11? Actually makes sense? Wow, you guys are so smart that even when I don't explain it well, you understand it. Ooh. That takes the pressure off. All right. Yesterday, where is it? Oh, naturally I didn't save it on here. Yesterday, I could have sworn I typed this in somewhere. Oh well. Yesterday you did this, right? Page 154, 1 through 3, 6 through 11, 15, 16, and 18. Today, add that.